Have you ever wondered how your phone instantly recognizes your face? Or how doctors can detect tumors in medical scans with incredible accuracy? The answer lies in one of the most powerful tools in artificial intelligence, convolutional neural networks, or CNNs. Hey everyone, welcome back to AI Academy, and today we're diving deep into CNNs, the technology that's revolutionizing computer vision. By the end of this video, you'll understand exactly how these neural networks see and process images just like our brain does. If you're new here, don't forget to hit that subscribe button and the bell icon for more AI content. So, what exactly is a convolutional neural network? Think of it as a digital brain specifically designed to understand images. But here's the key difference from regular neural networks. Traditional neural networks treat images as flat lists of pixels. Imagine trying to understand a painting by looking at each brushstroke individually, completely out of context. That's not how our eyes work, right? CNNs, on the other hand, maintain the spatial relationships between pixels. They understand that nearby pixels are related, just like how your brain recognizes that eyes, nose, and mouth together form a face. The CNN has three main superpowers. First, it uses convolution to detect features like edges and shapes. Second, it uses pooling to focus on the most important information. And third, it connects everything together to make final decisions. Let's start with the star of the show, convolution. Imagine you have a magnifying glass that can only see a small portion of an image at a time. This magnifying glass is called a filter or kernel. This filter slides across the entire image pixel by pixel, looking for specific patterns. For example, this filter here is designed to detect vertical edges. Here's how it works. The filter multiplies its values with the pixels underneath it, adds them all up, and produces a single number. This number tells us how much that pattern matches what the filter is looking for. But here's where it gets really cool. We don't use just one filter. A typical CNN uses dozens or even hundreds of filters, each looking for different features. Some detect horizontal edges, others vertical edges, some look for curves, corners, or even complex patterns. The result of all these convolutions creates what we call feature maps, basically highlighted versions of the original image showing where different features were found. Now, after convolution, we need to add some nonlinearity to our network. This is where activation functions come in, and the most popular one for CNNs is ReLU, Rectified Linear Unit. ReLU is beautifully simple. If a value is positive, keep it. If it's negative, make it 0. Why do we do this? ReLU helps the network learn complex patterns and prevents the vanishing gradient problem during training. It also makes computations faster since we're just zeroing out negative values. Next up is pooling. Think of it as creating a summary or compressed version of our feature maps. The most common type is max pooling. Max pooling takes small regions of the feature map and keeps only the highest value. It's like saying, in this area, the strongest feature detected had this intensity. Pooling does three important things. First, it reduces the size of our data, making processing faster. Second, it makes our network more robust to small changes in position. Whether the cat's eye is 2 pixels to the left or right doesn't matter. Third, it helps prevent overfitting by reducing the number of parameters. Now let's see how all these pieces fit together in a complete CNN architecture. A typical CNN looks like a pipeline with several stages. We start with our input image. Then we have multiple convolution layers, each followed by activation functions and often pooling layers. Notice how the images get smaller but deeper as we go through the network. Here's the beautiful part. Early layers detect simple features like edges and corners. Middle layers combine these to detect more complex shapes like curves and textures. Deep layers recognize high-level concepts like eyes, wheels, or entire objects. Over the years, researchers have developed various CNN architectures. Linnet was one of the first. AlexNet brought CNNs into the spotlight. VGG showed us deeper is better, and ResNet solved the problem of training very deep networks. At the end of our CNN, we have fully connected layers. These are like traditional neural network layers. But first, we need to flatten all our feature maps into a single vector. Think of it like taking all the detected features and creating a list of them. The fully connected layers then use this list to make the final classification decision. For example, if we're classifying cats versus dogs, the fully connected layer might learn that pointy ears plus whiskers plus small nose is probably a cat, while floppy ears plus big nose plus larger size is probably a dog. So how does a CNN actually learn? It's all about the training process. We start with random filters. The network literally knows nothing about images. We show it thousands of labeled examples. For each image, the network makes a prediction. We calculate how wrong it was using a loss function, and then we use backpropagation to adjust all the filters and weights to make better predictions next time. This process repeats thousands of times. Gradually, the filters learn to detect meaningful features, and the network gets better at classification. To improve training, we use techniques like data augmentation, rotating, flipping, or slightly modifying our training images so the network learns to be robust to variations. CNNs aren't just academic curiosities, they're powering the technology around us every day. In healthcare, CNNs can detect cancer and medical scans, often more accurately than human doctors. They're analyzing X-rays, MRIs, and CT scans to save lives. Self-driving cars use CNNs to understand their environment, detecting pedestrians, other cars, traffic signs, and road markings in real time. Your social media platforms use CNNs for automatic photo tagging, content moderation, and even generating those fun filters. Security systems use them for facial recognition and surveillance. Artists are using CNNs for style transfer, creating art that combines the content of one image with the style of another. We're even seeing CNNs in agriculture, detecting crop diseases and optimizing farming. Like any technology, CNNs have strengths and weaknesses. Let's be honest about both. The advantages are impressive. They achieve human-level or better performance on many visual tasks. They automatically learn features without manual engineering. They're robust to variations in lighting, position, and scale. But they also have limitations. They require massive amounts of labeled data to train properly. They need significant computational power. They can be fooled by adversarial examples, images specifically designed to trick them. And they're often black boxes. We can't always understand why they made a particular decision. Ready to try CNNs yourself? Here's how to get started. Frameworks like TensorFlow, PyTorch, and Keras make building CNNs accessible to beginners. You can start with pre-trained models, networks that have already been trained on millions of images. Transfer learning is your best friend when starting out. Take a pre-trained CNN and fine-tune it for your specific task. It's like having a head start in a race. Practice with popular datasets like Cypher10 or ImageNet. There are tons of tutorials online, and many are free. Start simple, maybe classifying cats versus dogs, then work your way up to more complex projects. Let's recap what we've learned today. CNNs are specialized neural networks that excel at image processing. They use convolution to detect features, pooling to summarize information, and fully connected layers to make decisions. They're trained through backpropagation and are powering incredible applications across industries. The future of CNNs is exciting. We're seeing advances in efficiency, interpretability, and new applications we haven't even imagined yet. What's your favorite CNN application? Have you tried building one yourself? Let me know in the comments below. If this video helped you understand CNNs better, smash that like button and subscribe for more AI content. Check out the description for links to resources and code examples. Thanks for watching, and I'll see you in the next video where we'll dive into advanced CNN architectures. Until then, keep learning.